Welcome to CS1104 Computer Systems. This is the Unit 4 Lecture Part 1. During this unit, we're kind of moving away from what we've been talking about, which is the combination logic or combinatorial logic that we look at. And if you recall, what characterized this combination logic was the fact that I put a series of gates together and I put an input in and it produces an output. But what it doesn't have is it doesn't have this concept of state, where it's retaining values. Now, this becomes important because as we start getting into putting our ALU together, and from that ALU, other components such as the program counter and the clock, the registers, and the control unit itself, that we start to try to look at sequencing. And one of the things we're going to learn is that the clock is very important within a computer system. It essentially defines the intervals in time in which things happen. So the combinatorial logic reacts to the clock because, or it really doesn't react to the clock, I should say, because essentially whenever I apply a voltage to the circuit, then it reacts. The problem is that within a computer system, I do have this concept of time. I do have the clock that's going on. I do need to do things in a particular sequence. And that's where this idea of sequential logic comes in. I need to be able to retain state. And that is what makes sequential logic really different from the combinatorial logic that we've been looking at up to this point in time. So, sequential logic maintains state. And the way that it does that is that I have my chips or my structures. So I put my circuits together, and essentially those circuits are going to operate much the same way as we've seen before with the other circuits, with the exception that they have this one little feature here, which is this feedback loop. And essentially what's going on here is I'm saying I'm going to take the output and I'm going to put it back in as input. And essentially what that does is it doesn't, create a situation where I just have an input, I produce an output, and then it's over. What I'm doing is I'm going to hold on to that output because I'm going to push it back in as my input again. So essentially, by putting in this kind of feedback loop, I can actually maintain states, right? So I need to have this kind of a feedback loop. Now, whether it brings a problem, right? So if all I do is I kind of have an input and then it feeds back, essentially it gets locked into a cycle. So whatever I put in stays in, and I really don't have any way of changing it. So one of the things I need to be able to do in sequential logic is not only have the feedback, which maintains state, but I want to be able to control that feedback. I want to be able to determine when that occurs and when to stop it, and quite frankly, when to stop to start it, as well as when to stop it. So I need to be able to stop values from cycling around endlessly. So essentially what I need is those features. I need to be able to maintain state. I'm going to do that by using feedback. So I'm going to take the output and I'm going to push it back in as my input, and I'm going to hold values that way. But then I have to have the mechanism in place that allows me to kind of turn the switch off when I need to and get rid of that state or change what that state is. So very simple circuits that have state is this idea of a latch. And think of a latch as kind of a circuit that you switch open and you hold it open. So for example, in this particular circuit, this circuit, which is just two inverters, once I get that circuit going and I've applied the power to it, it basically is going to maintain this state forever. There's absolutely nothing that's ever going to change this state. So the state on the feedback over here is going to continuously be 1, and the state on the other is going to continuously be 0. And they feed each other. And I can use this kind of a concept to actually create a memory cell. Right? So imagine, if you would, that I have some data out here. Maybe it's a value coming in that's a 0, or maybe it's a value coming in that's a 1, right? So I might want to come in here and say, hey, I want to remember that value. And I can do that with kind of this remember switch. When I close it, it essentially creates that feedback loop, that mechanism that says feed the input back in, so I give this continuous cycle going on and on and on. But, of course, I can actually open the switch at some point in time. When I do, it allows me to set another value or to lose the value, to reset what it is. So this is what we mean by this idea of the ability to selectively break out of the feedback path. I also have this idea of a load switch, right? So I don't want to be loading the data all the time. I don't want to be continuously changing the value that's in there. I want to selectively be able to do that. Now, what you're going to see as we start looking at different memory circuits, they're all going to have this kind of feature set. It's going to have some ability to control when I load something. So when I'm going to be able to change the value that's held in the memory cell, and also this ability to kind of create that feedback loop and cut off that feedback loop when required, allowing me to memorize a piece of information. So how do we do that, right? And basically what we're going to see over here is we have a model, if you would, of a memory circuit. And this one's going to be based essentially on what we call a data flip-flop, and we're going to look at that in just a moment. But you'll see that what we have here is we have a in, or our load portion of it, which is data comes in here. We have our output, which is our ability to read that data, what's coming out, and then over here I've essentially got my switch. And this switch in this simple circuit essentially says, when I turn this on, it allows me to load a new value, and when I turn it off, I cannot load a value. And this switch down here, this control, which normally I'm going to attach to the clock, right? This is how I am allowed, or how I have the opportunity to actually change the value. Okay? So I mentioned that what this is based on is this idea of a flip-flop. And you go through your reading material, you're going to see what the actual structure is of a flip-flop in terms of the gates. So what's inside of this memory cell, you can kind of look that up. And what you're basically going to see is we have a couple of and OR circuits, and you will definitely see this idea of the output of the one becoming the input to the other, creating that kind of memory circuit. And how I use this circuit is very varied within the computer system. So anytime I have something where I have to remember state, I use this kind of circuit. Now, there's two main usages. One of it is up here, which is registers. The other one is something we call RAM. So we might all know that RAM stands for random access memory. And essentially the real difference between the register and the RAM, and we're going to look at both of them when we look at architecture in a unit or so from now. But essentially the register, imagine that I have a series of 1-bit memory cells. So each of these, for example, this is a 1-bit memory cell. And I can put them together, and let's say, for example, that I'm working with a computer architecture that has an ALU based on using 8-bit numbers. So to have a register, and what that register is going to do is it's going to store a number for me. It's going to store a binary number. So I would actually have to have 8 of these cells put together sequentially. And it essentially, its function is that it allows me to hold data between cycles of the clock. Okay? And essentially, that's a register. A register is basically one number for whatever the width of the data is. RAM relies upon the same kind of logic. It's using the same kind of memory cell. But what happens in the case of RAM is I put these memory cells together in large groups or in arrays. So, for example, I might have a whole series of them representing, a whole series of these memory cells representing each of the bits in a word for whatever the size of the architecture is. Maybe I'm working with 8-bit CPU or a 16-bit or a 32-bit. Throughout much of our assignments, the ALU that we're going to be working on and working with, that's defined within the text, is actually 16 bits. But essentially, each of these memory cells holds 1 bit. I might have, let's say that there's 8 of them, so this might be 1 and this might be 8 over here. That's really a poorly drawn 8. This is 1 and this is 8 over here. All of that makes up one word. Well, that would be a register. Just one word worth of the memory cells. Now what I do within RAM, however, is I actually have multiple of these sets of registers. And I can address them through a decoder. So I create an array of bit cells for the size of the word that I'm dealing with, and it may be many, many, many long. So, for example, in the example that we're using in the book, when we get to start using the CPU emulator, or the simulator, I should say, I believe that it actually has 24,000 of these groups of 1-bit cells organized in 16-bit words. So it winds up being a lot of these gates. In fact, when you start hearing about the fact that some of the modern CPUs are literally comprised of millions of transistors, you can start to get a sense of how and why we use so many of those transistors, particularly when you start thinking about how much statefulness that we have in that CPU, and all of that state is actually created or maintained, if you would, through the use of these registers, or these memory cells put together into registers, and the registers, or groups of memory cells I should say, are put together in long arrays to create RAM.